Okay, so if the reality of modern artificial intelligence means these systems that learn, adapt, handle really sensitive operations, then we're just not dealing with simple software security anymore, are we?
Not at all.
We're talking complex, highly targeted cyber threats, ones that exploit the nature of how these models get and process knowledge.
Exactly.
And if AI is going to run like significant parts of our infrastructure, well, we need a solid playbook, right? A comprehensive one. And thankfully, it looks like Europe is drafting something that goes way beyond standard IT security.
Mm.
Our mission today is a deep dive into this draft standard, ETSI EN 304223 V2.0.0. It's called Securing Artificial Intelligence, or SAI.
Yep.
And this isn't just like a set of recommendations. It sets baseline cybersecurity requirements,
Yeah.
binding ones, for all sorts of AI models, neural networks, generative AI, the works.
We're basically charting the security roadmap for the entire AI lifecycle.
Mm-hmm.
And what's really interesting here, I think, is that this document, it just fundamentally rejects treating AI security like, patching Windows or something.
Right.
Instead, it systematically goes after the unique security risks. Risks specific to AI tech, things that come up because of how much they rely on data and inference.
Okay, let's unpack that a bit. Before we get into the nitty-gritty, what's the sort of core philosophical difference here? Securing, say, your online banking app versus securing an advanced AI.
Well, think about it. Traditional software, it's predictable code, right?
Mm-hmm.
Built on rigid logic.
Yeah.
AI, though, it's more like emergent knowledge. It's built on massive amounts of data, on inference. So your attack surface isn't just the application code anymore.
Ah, okay.
It's the training environment, it's the data pipeline, the model itself is a target.
Gotcha.
And because of that, AI brings in totally distinct security risks, like data poisoning.
Oh.
That's where someone deliberately slips malicious data into a training set. The goal is to compromise how the model behaves later on.
Yeah.
Think of it like, I don't know, a saboteur putting bad ingredients into a huge industrial recipe.
Wow. Okay.
And you also have things like the recently notorious indirect prompt injection, where an attacker embeds a hidden command inside maybe an image or a PDF, something the AI reads later, and then bam, executes the command. Traditional software just wasn't built for these kinds of knowledge-based attacks.
And because AI isn't just a one-and-done deployment, it's more like a continuous process, a living system.
Yeah.
The standard breaks security down into 5 mandatory phases, right? Mirroring the whole life cycle.
Exactly. Secure design, secure development, secure deployment, secure maintenance, and finally, secure end of life.
Covers everything.
It tries to. But before we dive into those phases, we really need to clarify who's responsible for what. Because securing AI, it really relies on cooperation.
Makes sense.
Responsibility is heavily distributed across the supply chain. The standard is pretty clear defining these stakeholders.
Okay.
So first, you've got the developers. They're the ones creating or maybe adapting the model. Often they're the AI providers under rules like the EU AI Act.
Okay.
Second, the system operators. They take that model and actually deploy it, maintain it within their own infrastructure.
Right. And then crucially, there are the data custodians. Why the need to separate the custodian role from, say, the operator or the developer?
Good question. It's because the custodian controls the permissions and, importantly, the integrity of the source data.
The crown jewel.
Pretty much, yeah. It's the AI's most valuable asset and often its biggest vulnerability. And this group, the custodians, it might be multiple different entities, internal departments, managers of public data sets, you name it. Separating the role forces specific accountability for data integrity.
Okay.
And then we also have end users, obviously using the system, and maybe less obviously affected entities.
Implicit entities.
Yeah, people. Or even other technologies that don't directly interact with the system but are affected by its decisions or outputs.
Yeah.
That's a massive scope increase compared to usual security thinking.
That clarity is vital, yeah, when you start assigning who has to do what. Okay, let's start at the beginning then. Phase 1, secure design.
Right.
Principle 1 is about raising awareness of these new threats. Sounds a bit basic, maybe, but the specifics seem tailored for AI.
They are. It's not just general don't-click phishing links training. Organizational cybersecurity training must be tailored to specific roles.
Like?
Well, a data custodian needs training on data standardization techniques, maybe. A developer needs secure coding practices specific to AI algorithms, how to prevent certain vulnerabilities.
Ah, okay.
And critically, this training has to be updated regularly, especially, the standard says, if new substantial AI-related security threats emerge. You can't just rely on last year's training module. It moves too fast.
No resting on laurels. Okay, principle 2 then. Designing for security right alongside functionality and performance from the start.
Yeah. And the key provision here, it uses that strong word, shall. Developers and system operators shall ensure AI systems are designed to withstand adversarial AI attacks, unexpected inputs, and system failures.
With a stand. That sounds tricky for something non-deterministic.
It is tricky. That's why the standard also mandates a clear audit trail,
Yeah.
documenting the operation, the lifecycle management of models, datasets, prompts, everything. So you can trace things back when, inevitably, some weird happens.
Forensics.
Okay.
Now, principle 3. This is where it gets really interesting for me. Evaluating and managing threats. What specific kind of AI native attacks must be included in threat modeling? The stuff standard IT threat lists might miss.
Right. So we're looking for techniques designed to basically steal the model's knowledge or corrupt it. Threat modeling has to be regularly reviewed and updated to address things like data poisoning, which we mentioned,
Yep.
but also model inversion and membership inference.
Could you quickly define those last two? They sound quite specific.
Sure. So model inversion is where an attacker tries to figure out properties of the original training data just by analyzing the model's outputs, like trying to reverse engineer what the model learned,
Yeah.
maybe even reconstruct some data points.
Ooh, okay. Privacy implications there.
Huge ones. And membership inference is maybe even more insidious. That's trying to determine if a specific individual's record was actually used in the training data set.
Yikes. Okay, so the threat modeling has to account for those. What if, say, a developer finds a flaw in a foundational model they're using, something inherent, maybe unavoidable, and they just can't fix it?
What does the chain of responsibility demand then?
The standard is very clear. Mandatory communication. The developer shall tell the system operator about that unresolved threat immediately.
Okay.
And then the system operator shall communicate that information promptly to the end users. And it's not just a vague warning. It has to include details on the risks, potential impacts, and importantly, recommended actions the user can take to address or monitor the threat.
So the buck doesn't stop with the developer.
Absolutely not. Accountability flows downstream.
That feels like a fundamental shift. Okay, last one in secure design. Principle 4, enabling human responsibility.
Yeah, this is all about human oversight, designing systems so their outputs are explainable, or at least interpretable. Why is that so critical?
Well, if a human is ultimately responsible for assessing the output, maybe it's an AI suggesting a medical diagnosis or financial decision, that human needs enough context from the system to make an informed, auditable choice. They can't just trust a black box.
Right.
And part of this is also making end users aware of prohibited use cases, being transparent about what the AI shouldn't be used for.
Okay, that wraps up design. Moving into phase 2, secure development and the supply chain. Principle 5 talks about identifying, tracking, protecting assets. The complexity here must be, well, huge.
It really is, because AI assets aren't just code. You've got massive models, potentially sensitive data sets, so disaster recovery plans, for instance, they have to be tailored for specific AI attacks.
Not just restoring from a backup.
Not quite. You need to ensure you can restore to a known good state. That means verifiable model weights, data integrity checks, things that can resist, say, a poisoning attack that might have subtly corrupted your backups over time.
Wow. Okay, and what about handling data during this development phase, especially with continuous learning and tuning models?
Right. The standard says developers, data custodians, and system operators shall apply checks and sanitization to all data and inputs. And here's the crucial bit. This process must be repeated whenever model revisions are made, maybe based on user feedback or continuous learning.
Because that loop is where new vulnerabilities can sneak in.
Exactly. That continuous cycle needs continuous scrutiny. It's not a one-time check.
Makes sense. Okay, principle 6, securing the infrastructure, APIs, environments. Sounds like a prime attack surface.
It absolutely is. If developers offer an API to external customers, they shall apply technical controls to mitigate attacks. Things like placing limits on the model access rate.
Rate limiting. Why is that important for AI security specifically?
Well, it limits an attacker's ability to just hammer the system with queries. That kind of rapid-fire questioning is often how they try to reverse engineer the model or find weaknesses in its defenses.
Oh, okay.
And they also need dedicated, separated environments for development and tuning, especially if the training data isn't public. You don't want leakage.
Right. Principle 7, the supply chain. Now, let me stop you here, because this feels like where reality sometimes bites, doesn't it?
How do you mean?
Well, we know in software development, sometimes you kind of have to rely on an older, maybe unsupported component because the modern alternative costs a fortune or breaks everything else. How realistic is it to expect a system operator to justify using, say, an undocumented or maybe unsecured foundational model just because it's the only one that hits the performance target?
That's a fantastic question, and yet it gets right to the heart of practical compliance. The standard actually acknowledges that reality to some extent.
Oh, duh.
Yeah, it doesn't demand absolute perfection if it's genuinely impossible, but it demands mitigation. If an operator must use a component like that, they shall document the justification thoroughly, like proving there was no viable alternative. And crucially, they must apply extra mitigating controls and do a really thorough risk assessment.
So it's not a free pass, but an acknowledge and contain approach.
Exactly. It's not a flat-out ban, but they have to actively demonstrate they've taken steps to manage that specific risk.
Mm.
Oh, and another thing, under supply chain. System operators shall tell end users before they update a model, communicating their intention. Transparency again.
Okay, good. Principle 8 is documentation. Beyond the usual stuff, what's the most important security-relevant info that needs that audit trail?
Well, documenting the intended scope and potential failure modes is key. But I think the most critical shift is around traceability and integrity. Developers shall release cryptographic hashes for model components.
Hashes, like digital fingerprints.
Exactly. So others down the chain operators, users can verify the authenticity and integrity of the model they're receiving, make sure it hasn't been tampered with.
Smart.
And for tracing potential poisoning attacks, if public data was used for training, the source needs documenting, like the exact URL, the date and time it was scraped. These provide the digital breadcrumbs you need to go back and find where malicious data might have entered the pipeline.
Essential for forensics later. Okay, last one in this phase. Principle 9, appropriate testing.
Yeah, major testing before release, obviously.
Mm.
But specifically, developers need to evaluate model outputs to ensure they don't inadvertently leak information that allows reverse engineering of non-public stuff, like the training data itself.
Okay.
And also ensure the outputs don't provide unintended influence over the system itself. You don't want the AI's output to somehow trigger unexpected automation or execute commands it shouldn't.
Right, preventing self-escalation or something. Okay, so the model's built, tested, now it goes live. We're into phases 3, 4, and 5. Deployment, maintenance, end of life. Principle 10 is communication during secure deployment.
Yeah, and this one focuses heavily on the end user again. System operators must clearly convey, in an accessible way, where and how the user's data will be used, accessed, and stored.
Like, specifically.
Like explicitly stating if their inputs are going to be used for model retraining or if their prompt history might be reviewed by human employees or maybe external partners. Full transparency.
Got it. Principle 11, then. Maintenance, patches, updates, addressing that continuous learning loop again.
Exactly.
And the recommendation here seems pretty profound. Developers should treat major AI system updates almost like developing a new version, requiring a completely fresh security testing process.
That's the idea.
Yeah.
Because an AI update isn't just a small patch sometimes. It can be a significant change in the model's learned knowledge. It's like, well, maybe not rebuilding the brain, but significantly altering its connections.
So it needs a full security reevaluation.
That's the guidance, yes. Developers should also help system operators evaluate these changes, maybe through beta testing or versioned APIs.
Okay. Principle 12, monitoring system behavior on an ongoing basis.
Right.
And system operators need to analyze logs not just for the usual stuff like breaches or denial of service attacks, but to detect anomalies or unexpected behavior over time. The standard mentions things like data drift. Can you explain that for our listener?
Sure. Data drift is basically when the real-world data the model is encountering starts to look significantly different from the data it was originally trained on.
Okay.
Monitoring this drift is crucial. It can signal that the model's performance is degrading, sure, but it could also be a sign of delayed or really subtle data poisoning effects finally surfacing. Things look okay for a while, then start getting weird.
So you're looking for gradual changes, not just sudden breaks.
Exactly. Long-term pattern analysis.
And finally, the last phase, Principle 13, secure end of life.
Wrapping it all up.
This makes sure that if a model or its training data is decommissioned or maybe transferred somewhere else, the data custodians are involved and those assets are securely disposed of or deleted. It's mandatory.
Right. To prevent security issues or proprietary knowledge from leaking out or transferring insecurely to new systems or owners, closing the loop securely.
Wow. That was a truly comprehensive look, structuring AI security across that entire life cycle. It's not just technical rules, is it? It's a whole chain of accountability for these non-deterministic systems.
It really is. And I think the clarity in defining those responsibilities, who's the developer, who's the operator, who's the custodian, and then directly, mandatorily addressing those AI native threats, model inversion, membership inference, data poisoning, it provides a really solid, enforceable baseline, something adaptable for any organization dealing with these powerful technologies.
So what does this all mean for you, listening? Well, understanding the structure means you can start asking really critical, targeted questions about any AI system you might encounter or commission, even without deep technical expertise.
Yeah.
Questions like, how is the training data sanitized? That's Principle 5. Who ensures the model's outputs are interpretable? That's Principle 4. And maybe crucially, what is the disaster recovery plan, and is it specifically tailored for an AI attack like data poisoning, like Principle 5 requires?
Absolutely. And thinking about that last phase, end of life, it raises a really interesting, maybe slightly unsettling final question. It touches on the nature of knowledge itself, I think.
No, go on.
Well, the standard demands secure disposal, right? Secure deletion of models and data under Principle 13. But how does an organization truly ensure secure deletion? Especially when the underlying patterns, the learned knowledge, might still be latent, or maybe inferable using techniques like model inversion, but from other seemingly disconnected systems that interacted with the original one.
Huh. Like a ghost in the machine.
Sort of. You delete the model from one place, but the echo of its knowledge might still linger elsewhere, extractable perhaps. Just highlights the complexity. How do you truly delete something that has been learned?
The challenge of deleting knowledge itself. That is a fascinating thought to chew on. Thanks for diving into the source material with us today.